Litmus is an extract of which of the following? Sir, it's like lichens. C.
Hmm. Correct. Next.
Ant bite is treated by application of baking soda.
Baking soda. Good. Hmm. Okay, it's already 7 minutes past. They haven't joined yet. See, oil of vitriol is basically now you have a concentrated acid called as sulfuric acid. Okay, now so sulfuric acid, just like you have a base milk of magnesia is there that is called as blue vitriol.
Yes, sir.
So just like you have milk of magnesia, that is a basic substance, by the way. So you have
Yes.
sulfuric acid is also. Okay, now
Okay, sir.
so sulfuric acid is also known as the oil of vitriol because it looks like a dense oil and is produced from green vitriol. That is ferrous sulfate. So two terminologies are here. You have blue vitriol, you already know. In terms of acid, you have oil of
Sir,
vitriol.
can you repeat
That
again? What
is,
did you say?
I said that in bases, you have blue vitriol, right? That is used as an
Yes, sir.
antacid. So
Yes, sir.
sulfuric acid is there, and this is called as oil of vitriol. And it is actually
Okay.
extracted, it is produced from green vitriol. So you have one more
Okay, sir.
terminology here, that is green vitriol. And green vitriol is basically ferrous sulfate, that is FeSO4, and this is H2SO4.
Sir,
And it is,
FeSO4?
yeah, ferrous sulfate, that is ferrous sulfate.
Okay, sir.
Okay, now both have similar number of radical charges on them, so thereby it is FeSO.
Uh, sir, but I have a doubt. There is an
Yes.
element, uh, like, how
Mm-hmm.
do we know which Fe we're talking about?
Okay, which Fe we are talking about?
Yes,
Like
sir.
we are talking about iron over here. I didn't got your question. Will you please repeat that again?
Sir, like, Fe means, like an element, like, which is, like, it, I mean, it is an element in the periodic table, right?
Mm-hmm. Fe, that is iron basically.
Iron, yes, sir.
Mhm.
So, like, how do we know which one we're talking about when, if it comes actually, like, in exams or anything?
Okay, ferrous sulfate. I think you are saying ferrous sulfate is like basically one is FeSO4
Yes, sir, the formula.
based on the formula.
Yes, sir.
Okay, okay. See, in the periodic table now, like you get to see, like for example, sodium. Sodium, it's not convenient for us to write the whole name in the periodic table sodium, right now. Or for example, it will
Yes,
be having a different name, like the origin of that metal or non-metal. Okay, the country in which it was basically discovered. So it will be having a name like that. For example, sodium is also called as
Na.
natrium. Natrium. So
Oh.
thereby its symbol came to be Na. Yeah.
Okay, sir.
Hmm. Or for example, you have like iron is Fe. Okay, now
Yes, sir.
iron, the symbol for iron is Fe. While
Yes,
for
sir.
hydrogen it is simply H. Oxygen it is O.
Yes, sir.
Right now. Or for any other,
Yes,
like for carbon it is simply C. But for
yes, sir.
particular elements, you will be having a different symbol because sodium is like natrium also. Right now, just like in English, just like you have Greek origin, you have Latin origin. So based on that, you'll be having it. Okay, now I hope you are able to understand this. Yeah.
Like, I understand the names of how they came and all, but I don't still get the meaning. Like,
Okay.
there are many chances that we might get confused, right? So, like, for example,
Mhm.
in an exam, if they mention this, for suppose, and they mention it, the formula, and they mention the formula, is it okay? I mean, it will be wrong if we mention iron, right?
Basically, like if I were to now basically write it like, how do you like it? Like ISO4. If you
No,
were
sir.
to write it like this, it will be obviously incorrect, because universally the symbol that is accepted for iron is Fe, right now.
Yes, sir.
So
Yes, sir.
like we have no option but to memorize that. Okay now. So like for helium, what is the symbol for helium? Like He.
He.
Okay, since just give me one moment. See, like for hydrogen it is H, right?
Yes, sir.
For helium it is He.
Yes,
For
sir.
lithium it is Li.
Li. Yes, sir.
Beryllium it is Be.
B. Yes,
Boron it
sir.
is B.
B.
Carbon it is C.
C.
Nitrogen and
N.
oxygen O. Getting it
O.
now? Or for
Yes, sir.
fluorine, like it is F,
F.
right? Or sodium it is Na,
N. A.
right now. So we either, like in these you can see like you are taking the first letter or first two letters of the element's name.
Yes,
But
sir.
in case of sodium we are taking Na. So why is it so we are taking Na? Because the thing is that Na, the full form of basically Na is actually natrium. Okay now. So just like I was telling you, like some of the elements have their Greek names also, some of them will be having their Latin name also. So I'm not sure whether this is the Greek or the Latin name, but in some other language it is pronounced as, it is written, sodium is written as natrium there right now. So thereby you are taking first two letters of natrium and that is Na. Getting it now?
So
Only
basically,
some of
based
exceptions are
on
there.
the question, based
Yes.
on the question, so basically based on the question, we have to know which, like, what they're talking about, whether it's ferrous sulfite or like another one.
Mhm. On
Because
that
like,
basis,
okay,
like natrium, as I was telling, I think this is the Latin name. This is Latin name of sodium.
okay, so
Okay, now so just like that, you have different symbols. For example, like sulfur, it is S. For chlorine, it is a Cl. For argon, it
so
is Ar.
I actually, so what I meant was that for ferrous sulfite,
Ferrous
you
sulfate.
wrote
Ferrous sulfate.
okay, ferrous sulfite.
Mhm.
You wrote the formula as the formula. You wrote FeSO4, right, sir?
Yes.
And I was asking if how would we know what they mentioned?
Okay. How would we know what they have mentioned here?
Yes, sir. That's what I was asking.
Okay. Okay. So what I can understand from your question now, ferrous sulfate. Okay. Okay. See, ferrous is referring to. We need to know that ferrous refers to iron. Okay, now iron is also of different types, like iron 1, iron 2. Let's keep that aside for a moment, right? So
Okay, sir.
ferrous is actually basically iron, that is Fe. The
Yes,
symbol of
sir.
iron is Fe. Sulfate is actually SO4,
SO4.
right
Yes,
now.
sir.
So sulfate you need to know, like in class 9 you will be understanding, you have like sulfates, carbonates, right now.
Yes, sir.
Like carbonates are CO3. That is
CO3.
what carbonates are right now. So
Yes,
certain
sir.
things you will be studying in class 9. So then that will be giving you a better picture, like what basically we mean by sulfate, carbonate, what are these things. Okay now. So I hope
Okay.
you are understanding it, right?
Yes, sir.
Hmm. And sulfate is basically formed when you have like a sulfur, okay now, and when it forms bond with 4 oxygen. This you wouldn't be able to understand right now, because you would be understand able to understand it when you will be understanding some more fundamental concepts in higher classes. This is
Okay.
4 oxygen atoms that have binded with one sulfur atom. So we
Okay.
write it as SO4. One sulfur, 4 oxygen, right
Yes.
now. So there is sulfur atom and there is oxygen atom, and together it is called as sulfate.
Okay, sir.
Getting it now?
Yes, sir.
Okay, hope that is clear. Okay,
Yes,
has
sir.
no one else joined yet?
No, sir.
Where are others, by the way, today? Let me see the message if I've got any message regarding that. Not yet. Okay, so we have finished this chapter. So, Chakrika, do tell me, uh, was there any other chapters which you haven't studied in the batch?
Yes, there are
Uh,
still, I think, three more.
which one?
So there are physical and chemical changes.
Okay, physical
Fiber to
and chemical changes. Okay, yeah, fiber to fabrics, that is also there, right? Hmm.
Yes, sir.
Okay, so how about we revise this chapter of physical and chemical changes today?
Sure, sir.
Okay, now as you can see, these are the slides uh, from the class where we are doing this chapter. Okay, now. Okay, like you have a very classic example where you can see physical and chemical changes both. Like when you are burning a candle, when a candle is
There
burned,
is a physical change.
in fact, chemical change is also happening there.
Yes, sir, because the thread of the candle, it will
But
turn into ashes, and it's
correct,
not reversible. So
it's not reversible. Very good. While also you get to see the paraffin wax in the candle, it is also evaporating. That is also burning, right? So that
yes,
can also not be. We can also not get that back. So physical changes is happening in chemical changes. In physical changes, paraffin wax. By the way, paraffin wax is obtained from the refining of petroleum. Okay, now when petrol is refined, okay, now when fractional distillation of petrol is done, so thereby from there you obtain paraffin wax. Okay, now Chakrika,
okay, sir. Yes,
you are understanding what I'm saying.
yes, sir. Yes, sir.
Hmm. So it is one of the petrochemical. Anyways, so paraffin wax is melting due to the heat, and it again solidifies. That's why you get to see that on the sideways of the candle, it will be like this. So physical change is happening there. While the thread that has burned, while the paraffin wax that has evaporated, so that is the chemical change. Okay.
Okay, sir.
Anyway, by the way, why is it so that when you burn a candle, you are getting flame, but when you burn a coal, you're not getting flame? Why is it so that when we burn a candle, we are getting flame, but not
So
in
because
coal?
the coal is already burnt,
Coal is already burned.
like we get coal when it's already like burnt, right?
Okay. Further.
When we burn the wood,
Okay. What about the candle?
uh,
See, basically, the thing is
so
that,
even if it smells, we can even solidify it and create into a shape, and then still we can use it.
see, the basic thing here is now that whenever a fuel upon burning gives off vapors, so then it will be producing flames. I mean to say that when you are burning the paraffin wax, so the wax is actually turning to wax vapors first. Okay, Chakrika. It is
I think I get it,
actually
sir.
first turning into wax vapors. Yeah.
Yes, sir. Yes, sir.
So then the vapors are burning. So that's why you get to observe flame in that. Okay, now. While in the case of the candle, in the case of coal, so you are not getting it
Good
because
evening,
the
sir.
vape. Good evening, Sandus. Because
Sorry, I was late. Actually, I was outside.
okay, okay, no issue. By the way, we have no started revising the chapter, physical and chemical changes. Okay, no. Just moments ago we have started this chapter. By the way, so see, in the case of burning of coal, coal is already dry,
Yes, sir.
so it will not be giving off any vapors right now. Or also, if
Yes.
there is slight amount of moisture, so light amount of gas is locked inside the coal, it will be coming off. So initially it will be giving some flame initially, but after some time it will not be giving flame. Getting it now? So
So,
Sundar, the question was, no, Sundar, That why is it so when a candle is burned, we are getting a flame, but not in the case of burning of a coal? So thereby I just explained that when you burn the candle, wax starts turning into vapors of wax. So wax vapors are burning, hence you get the flame. While the burning of coal does not gives off any vapor, hence no flame. Yeah.
Yes. So, sir, it's only between the candle and the coal, right? Not everything is that way.
We have other examples also. For example,
But
take
like
the
not
liquefied
everything
petroleum.
is that way, right? Because like we also have paper, and paper does not produce any vapor like of petroleum or anything. So
Exceptions are there. Right, we will be having exceptions, but in general, we
okay,
are having so many examples. Okay, now. So see, for
okay,
example, liquefied petroleum gas. So you have
yes,
stored the petroleum gas at a very high pressure. So inside this, it is in liquid state.
yes, sir.
Inside the cylinder, it is in liquid state. Now, as soon as it comes out of the pipe and goes into the burner, so what you see, there is a pressure
Yeah,
difference here.
yes, sir.
First thing we see, the
Diffusion.
pressure difference is seen, right? Inside there was high pressure, and outside that when it comes in the air, there is low pressure. So whenever liquid from the cylinder comes into the air, it experiences low pressure. So thereby it converts into gaseous state. Getting it what I'm trying to say here?
Yes, sir.
Sundus, you got it? Hello?
Mm, yeah,
Did you
I
got
didn't
this
get
what I just said? See,
mm,
inside the cylinders, look at the full form of LPG, and it is liquefied petroleum gas. You have liquefied it under high pressure, right? So when it comes and inside the cylinder, there is high pressure, and when it is also it is a liquid state inside the gas inside the cylinder. As soon as it is comes out of the burner, it is now turning into the gaseous state because of pressure difference, because here it is low pressure. So know this thing down, that when you will be pressurizing the gas, when a gas is pressurized, it converts into liquid state, right? If it will be having moisture in it, it will be converting into liquid state. While the pressure is released, it will again turn back into the gaseous state. Let me tell you. See, you all must have seen a piston, or you might have seen syringes also. Obviously,
yes.
syringes.
Yes, sir.
So in syringes, you get to see that. Let's say this is the uh, let's say this is liquid. That is a needle. So when you are pushing it now, why is it so that, see, this is air, this one, let me point towards this one. So that is empty space. This is this is liquid in it. This is liquid in it. So you get to see that when you press it now, when you press it, what you get to see, that liquid comes out of the needle. Okay, that is how it basically functions. Now take a piston. You have taken a piston, and now you are pressing the gas molecules inside it.
So, what is a piston?
Piston is basically a setup like this, in which you get to see now basically like a syringe. So syringe is such a setup where you are basically compressing the air, and air is further pushing the liquid out of the needle.
So basically, so piston is a larger version of syringe.
Both are basically syringe is a type of piston. Syringe is a type of piston. Okay, now.
Okay, sir.
So that is the thing. So what I'm trying to say, that when you pressurize the gaseous molecules now, when you are pressurizing the gas molecules, and let's say there will be some moisture in it also, so it might turn into liquid. It might turn into liquid. And when you will be releasing the pressure, when you keep it out, when you release the pressure, so thereby it might again turn back into the liquid state. So there is a pressure difference under the gaseous molecules, where earlier the gaseous molecules were under high pressure, so thereby it converted into liquid state. Now when you release the pressure, it will again turn back into the gaseous molecules, into the gases state. So that is what is happening over here as well. Getting in what I'm trying to say? Did you guys got this or not? Hello?
So can you explain again?
Sure. See basically how it functions. When gas is compressed, so thereby what is happening is, say this is the gaseous molecules and they are at some distance from each other. Now what happens? You are compressing them. So let's say you are compressing it. So what will happen? The molecules of the gases will start coming closer like this. And we know that in liquids, the molecules are somewhat closer to each other. In solid, they are very compactly packed. Getting it now? While in gases, they are free to move. Right now? So this one, here you get to see that the gaseous molecules are under pressure. So thereby they will be compressing and turning it into liquid state. Getting at what I'm trying to say?
Yes, sir.
Another thing which we have observed here, that this is experiencing low pressure because you have not pressurized it. While here you have pressurized it, so thereby they are under high pressure. Is that clear?
Yes, sir.
Okay, no?
Yes, sir.
So that is the thing here happening. So once you will be releasing this, weight out of it now, so thereby what happens, the molecules of the liquid will again start to expand right now and then again turn back into the gaseous state. Okay, no? By the way, the piston, you might have heard this word earlier also, and pistons are used in engines also. You might have seen it in the engines, like it will be looking like
Sir, I
this.
think I did.
Yeah,
I
you
think
have.
I did.
You might have seen it like or read about it. Basically, it is found in the engines right now. So it's the system basically like this. Let me give you a diagram of it basically. See, there are different components in a piston. Okay, now for example, there will be a pump that will be pumping the, either it will be pumping the gas or either it will be pumping the liquid. Okay, no, so that is how it basically functions. So
Sir,
this
liquid in the petroleum.
petroleum, like in the car engines, will be having petroleum right now.
Okay, sir.
So that's where it is used. Anyways, to the chapter of physical and chemical changes. In this, basically, we will understand that what happens if some materials are brought under some changes. Either they might be experiencing a physical change or either they might be experiencing a chemical change, right? So when a material goes under some changes and if it retains its physical property, right? Basically, the composition of the material, if that does not changes, so thereby it is called as physical change, right? For example, you take a paper, you tear it into pieces. You are boiling water, so thereby water is evaporating and you put a plate over the boiling water. It again will condense back into water. Getting it now? Or you are mixing different substances together. For example, you are mixing um, sand and rice. So has the property of the two substances changed here? Yes?
No, sir.
No?
No.
Or you break a glass. Will the property change?
No, sir.
No. So you get to see that when you do these things, you crush a can, when you observe the melting of an ice or dissolving sugar in water, all these are examples of physical changes, right now. Okay, sublimation of dry ice is also there. What is sublimation of dry ice? In fact, what is sublimation first of all? Sublimation is that when a solid substance directly changes into gaseous state without going through the
Uh,
liquid phase.
so, but dry ice itself is a
Hmm.
physical change. I mean, like
Dry ice is
basically,
basically
dry ice is the example of sublimation, right?
dry ice is an example of sublimation, and dry ice is basically solid carbon dioxide. Okay, now dry ice is basically solid carbon dioxide. Okay, now you might have
Okay.
seen the dry ice. Like there are several uses of it
Yes.
right now. Like it can be used to keep the food cool right now. It can be used in the aircraft also, like where refrigeration you can't refrigeration system is not available there in the aircraft. So there, in order to keep the food cool, dry ice is used. The dry ice is so cool that you won't be able to keep hold it in your hand. Okay, no. So that is what
But
dry ice
I
is
mean,
there.
we
Yes,
can hold it, but not for a long time.
but not for a long time, basically.
Yes.
Right now. Mhm. Nitrogen balls, you might have seen that. That is also having a very cold temperature. Yeah. On stages in different concerts, on stages, we see that dry ice is used. Okay, no. So basically, in order to cover the floor of the stage, so thereby dry ice is used. Why is it so? Because it creates fog. Okay, no. So there we will be using it anyways. The first image, does these things are they related to physical or chemical changes? What type of what do we understand from this? Sight, a sense of hearing, sense of feeling. So these are neither physical, neither chemical changes, right? Okay. So when we talk about physical changes, we should be aware of the physical properties of the substances also. Like what are the physical properties of a substance? Its color, right? Size of the given substance, the volume occupied by the substance, right now, or the
Shape.
density of the given substance, shape. Very good, Sundus. So these are the physical properties, right? So when an object experiences some force or some change, um, some external influence, and if it retains the property, like um, if it retains the chemical property, like the composition does not changes, so thereby it is the physical change. Okay, for example, see, this blade has been heated here. Okay, now after some time when you stop heating it, it will again cool down, right? So the color here has changed. It has become it is very heated now, but is there
Oh,
any
but
change is the composition of the blade here? Yeah, Shikrika.
nothing, sir. Nothing, sir. Go.
Okay, so that is what physical change is there. Okay, no. Also look at this one also, by the way. Okay, now see, in this one you get to see that the state is happening. So from one phase, the matter is going to another phase, right? Solid to liquid, liquid to gas, and then back. So what is happening here? When it goes in the forward phase of change, like from solid to liquid and then gas, it will be absorbing energy. Okay, now it will be absorbing energy. For example, like you have to heat the solid in order to convert it into liquid, right now, and the liquid also further you have to heat it. Take the example of ice cubes. So ice cubes have to be heated in order to melt it, or either it will be absorbing temperature from the room, from the surrounding. Getting it now? Further, you have to boil the liquid in order to convert it into gaseous state, or you can simply see that if you were to leave the liquid open in your room for some time right now, so you get to see that it will start to evaporate. You take a glass and pour some water in it. After 1 week, you will see that water will be here. So why is it so? You were not heating it, but still the water level has gone down. Because the thing is that at room temperature also evaporation takes place. All right. So the basic thing I'm trying to say is here that when you are physically changing, so thereby energy is absorbed. When you change liquid solid into liquid and liquid into gas, energy is being absorbed. When you reverse the process, energy will be released. Getting it, Sundus and Chakrika, right?
Yes, sir.
So when physical changes takes place and the matter and the state of the given matter is changing, so either energy will be absorbed or released. I gave an example also. For example, the gaseous molecules of the water, let's say they are having an energy of 100 joule. When you convert that into liquid, it loses 20 joule. So thereby it is having 80 joule of energy. Joule is the unit of energy, by the way. Okay, now? And then
So can
again,
you
when you, this capital J, which is joule, it is a unit of energy. Okay, now? More specifically, it is a unit of heat energy. Getting it, Sundhu and Chakrika?
So is it the SI unit?
This joule,
Yes, sir.
no, I don't think this is the SI unit. I don't think. So you can see here that the change is happening in energy of the uh, given substance. And the reverse is also true. Like here it is at 60 joule at the solid state. And as you move towards the gaseous state, it keeps on getting more energy. By the way, these values which I have taken here, this is only for making you understand
I'll
the
just
concept.
come back in a minute.
Yes. Okay.
I'll come back in a minute, sir.
Okay. Okay. No issue. Yes, Sundar, so you're getting it or not?
yes, sir.
And the question here is that give one example of each kind. Show that a change in energy takes place when a physical or a chemical change occurs. So you have to give an example where you have to show that change in energy is taking place, right now, when a physical or chemical change is happening. Not only in physical changes, later on you will get to see that in the chemical changes also, energy change will be taking place, right? So change in a state, for example, energy change is taking place. Energy change is happening when a solid absorbs heat in order to melt. The previous example which we just discussed moments ago, right now.
Yes.
Of you can understand it in this manner also. Like for example, when you hold some ice cubes, when you are holding ice cubes on your hand, so why do you feel very cold?
So
Why is
what?
it
Sorry.
when you hold some ice cubes on your hand? Why is it so that we feel cold?
Because of the heat in our hand.
Because the ice cubes are absorbing heat from our hand. Okay, no? So their energy is being absorbed by it, right? Okay. Now consider another example of photosynthesis.
Sir, I can't hear you.
Okay. Am I audible to you, Sundus, by the way?
Yes, sir. You're audible.
Now we are
Uh,
audible, sir.
Okay. So you have example of like a photosynthesis. So photosynthesis, there which type of energy is changed? The light energy is changed into chemical energy. The light energy that is absorbed from the sun, and then thereby it is changed into the chemical energy, that is carbon dioxide is produced, oxygen is produced. Getting it now?
So, sir, then evaporation is also an example.
Evaporation is also an example of energy change. As you are heating the water, so water is changing into the gaseous state. So it is actually absorbing the heat, right now. Heat energy. By the way, energy, it is actually joule, which I was telling moments ago. It is actually the SI unit, guys. Okay, now I thought about something else. So joule is the SI unit of energy. Okay, now Chakrika and Sundar.
Okay, sir.
Yes.
Right. So energy change. Moments ago we discussed it in case of water, that energy is changing here. Water when melting, it requires energy, right? And water when it is freezing, it releases energy. That's why you get to see that at the back of the refrigerator, it releases some amount of heat. Or you have example of like air conditioners. huh? In air conditioners, what is happening basically? In air conditioner, what is happening basically? The heat of the room is basically being taken away from, it is being basically sucked up by the air conditioner, and by the compressor it is released, right now. So there, what is basically happening? It is making the air cool. So thereby, whatever heat is there in the air, it is being taken away by the air conditioner. So that can also be understood here. All right, now. So in context of that, we understood, and even when chemical changes will be taking place, there also energy will be changing. All right, now. So in both the cases, note this thing down, that energy change happens. Okay, now. So another question is that explain why there is an energy change in a change of a state of matter as well as in chemical change. So understand this thing, that when you have a given substance at let's say solid state, and when you look at the particles of the solid, they are very compactly tight, right?
Sir.
And as you go from liquid and then to gas, then the space between the particles increases and they are more free to move, right? Okay. Another term you guys need to understand here is that when a body is at motion, whether it be a body or whether it be the particles inside the body, when it is moving, so the type of energy that is being possessed by the body at that time, it is called as kinetic energy. Okay. So for example, in liquid, the molecules of the liquid are in motion because they have got some free space to move, while in the case of gases, they are more free to move. So as you move from solid then to liquid and the gas, thereby you will see that the kinetic energy of the particles will also be increasing. Getting it now, guys? So kinetic energy, can I say that in solid it will be lowest? Yes, Sundus and Chakrika? Since
The
particles
what?
are not in solid, kinetic energy will be lowest because the particles are having very less space to move about. Yeah.
Yes, sir.
While when we look at the liquid, particles are more free to move, and gases, they are maximum. They are having maximum amount of space to move here and there. Getting it now? Hmm. Now understand this one more thing, that since the particles of the solid are locked, since the particles of the solid are locked here, so thereby in order to make them make them free to move, you have to give more energy to it. So thereby solid will be absorbing heat. You guys are able to understand this thing or not? In order to uh, in order to make the particles of the solid free, you have to provide it with some energy. So thereby you provide it in the form of heat. So what happens? This is right now solid, and once you let's say this is ice. So once you heat it now, so thereby what happens? It starts to melt. Why is it so? Because now the particles of the solid have gained some energy, and then they will start to move here and then. They will start to move. And once they start to move, they will start to expand also. Hence, ice changes into water.
So it's basically the ice which gains some energy, right?
Exactly. The ice is
It
gaining
was
the
heat.
energy. Mhm.
But you were mentioning that it was heat which gained the energy.
Okay. Did I mention that? Okay.
Yes, sir.
Okay. Actually, I meant to say no, that the particles inside the ice are getting heated up. Okay. So once they have got heated up, so they will be gaining some kinetic energy. They will start to move here and there. And in the process of doing so, their state now changes from solid to liquid. Okay, no? So in this process, what is happening?
Oh,
Energy is absorbed in the form of heat. Getting it, Sundar and Chakrika, right? Now, when we look at the setup of molecules of the gases, now they are still far away from each other as compared to liquid, right? So we need to provide some more energy to the particles of liquid in order to make them gases, right now. So in this process also, heat is absorbed. Now again, you will be required to heat it in order to make it in gaseous state. So once you heat it more, now the particles will be gaining more energy. So thereby they will start to move more. And hence you are having the gaseous state of the water. Is that clear to everyone? You guys got
Yes.
this or not? Okay,
Yes.
no? Hmm. So this is where the energy is actually used up in order to break free the atoms, in order to break free the molecules of the given substance, right? So this is where the energy is used, right now. Or in higher classes, you will understand that there is a force that is binding all the molecules of the given substance. And in order to break free that force of attraction between the molecules, the energy is utilized there in order to break free the force of attraction between all these molecules of ice. Getting it now? Now see what happens. Once you reverse this process, once you are reversing this process, so thereby this is having extra amount of kinetic energy. Let me write this. This is having least kinetic energy. Okay. This is having more kinetic energy. And this is having maximum kinetic energy. Now, once you are reversing the process, once you are required to convert from the gaseous state, then into water, and then from the gases to the liquid state, and then to the solid state. So you have to reduce the kinetic energy of the particles, isn't it, guys? Yes. Are you guys able to understand this thing or not? Hello.
So I didn't get it.
Chakrika, what
so,
about you?
so me neither.
Mhm.
I was trying to figure it out.
See, basically what is now happening? Kinetic energy. Suppose someone is running on the street. So he is having kinetic energy. Okay. Or when we look at the particles inside this ice. So particles inside the ice are compactly packed. They're compactly packed right now. So thereby it is in solid state. Now, in order to become like a liquid state, in order to go into the liquid state, when I look at the composition of the liquid, I see that the particles are very far away from each other as compared to the solid right now. So what happens? You have to heat it. You have to heat it. You can understand it in this manner. For example, let's say that there is a prison. There is a prison, and in this you have some prisoners. So in this small room, let's say 100 of prisoners have been put into this small room, right? And let's say that they are not fed, they are not being fed properly. They want to break free from this prison. They want to break the prison, but they are not being fed up, so they are not having energy in their body in order to break these walls of the prison. Now, what if they were to be fed properly? They are being fed with a good food, so they will be gaining energy. Getting it now? So then they will be able to break free the walls of the prison, right now, and they will go to do different works, and they will be basically breaking out of the prison. Same reasoning, same thing can be understood here also. Like earlier, all the molecules of the ice are compactly packed. They want to break free, they want to become into liquid state, but in order to do that, they need some energy in the form of heat, right now, and then they will be converting into liquid state, right? So kinetic energy is basically giving them like food, right now. You guys are able to basically
Like,
heat
are
is
there only things which only need heat, and are there not things which are solid but need uh like,
Mhm.
for suppose we're using heat to melt what's in solid to change it into liquid,
Yes.
but can't we use the opposite? Like, can't we freeze it, or any, like, if we freeze it, it should turn into like, what do we say? It should turn into a solid or something.
No, look, basically what
Is
happens
there
now.
no chance like that to be converted into that way?
Okay. Look, the answer to your question lies in this, that when I look at the composition of the particles inside this, I see that they are very compactly packed, right?
Yes,
If
sir.
I were to bring down the temperature, if I were to cool it further, the particles will become closer to each other more and more.
So
It will
because of
become
the
more compact. Mhm.
but because of the closeness and because of more um more confined space,
Mm.
they can burst out something, right?
See, they will not be bursting up in that case. Basically, what happens? See, when you look at the solid, as I said, this is an atom, this is an atom. Okay, now this is the center of this atom. These are the center of the two atoms, let's suppose. Now, these two atoms will be pulling each other. These two atoms will be pulling each other. And there are so many atoms. There are so many atoms inside the solid that are pulling all of them each other. The nucleus of the atoms are pulling the nucleus of another atom. So hence they are in a state of solid. Now what happens? Okay, all the particles inside the solid, there is not sufficient space left inside the solid, and each of the space in all the atoms are basically pulling each other. So hence they are in a compact state. You can only make it in liquid state if the spaces between the atoms were to be increased. And how can we do that? We can do that if you were to provide them with energy. You were to provide them with energy in the form of heat. But if you were to cool them further, if you were to cool them further now, so after if you were to cool them further, you will get to see that the atoms will not be breaking free from each other. They will still be in a compact state, right? Because the purpose is that when you are giving them kinetic energy, when you are giving them energy, they come in motion, they start to vibrate, they come into motion, and only in that case they will be turning into liquid state. While if you were to freeze it further, it will become compact. Getting it now? Did you guys got it or not?
Yes, sir. Yes, sir.
Hmm. So the main thing is still left to be discussed. So I was actually saying, let me erase all these things. Anyways, see. So what I'm trying to say here now, just a moment. So I was saying that when you are converting ice into water, heat is absorbed and again heat is absorbed, right? And you get to see the kinetic energy of the particles is also increasing. Least kinetic energy, more kinetic energy, and then maximum kinetic energy. So in this process, heat is absorbed. Now, when you reverse the process, so maximum kinetic energy is possessed by the gaseous particle, and you have to convert it into liquid state, which is having lesser kinetic energy as compared to this. So energy will be released here now. Energy has to be lost. Energy has to be lost by the particles, isn't it? Hello, Sundus and Chakrika.
Yes, sir. Yes.
And again, when you will be converting it from liquid to the solid state. So as when you compare the water and the ice, which is having more kinetic energy, obviously water, because the particles of the water are more free to move here and there. So again, it has to release some energy. So when you are reversing the process, energy is released into the environment. Hope you guys are able to understand this thing. Is that clear to both of you or not?
Yes, sir.
Yes, okay.
Okay, no? So that was the physical change. So in physical changes, we have one important thing you can observe here, that although the state is changing, but the composition is changing. Is the composition changing? When you look at the ice now, when you look
No,
at the
sir.
molecular composition, it still is H2. Here also it is H2O. And here also it is H2O. Right now, Sundhu and Chagrika. So when
Yes,
the
sir.
composition of the given material does not changes, but density might change. As you can see, the density of the ice is more than that of the water. Density of the ice is different from water. Density of water is different from the gas. Getting it now? So that is another thing. Second thing, we get to see that the shape is also changing, size is also changing, the volume is also changing. Volume is increasing when you move from here to here, and in the opposite, volume is decreasing. So the physical aspects are changing, but the chemical aspect, that is the molecular composition, that is what changes. So that is what we know about physical change. While in the chemical change, what happens? New substances will be formed. Suppose you burn a paper, you have ash. So a new substance is formed. Can you obtain paper back from the ash? No. Can you get the wood back from the ash? No. Getting it now? So a change in which one or more new substances are formed, that is called as chemical change. And it is irreversible in nature in almost all the cases. Okay, now guys. Right? So in a chemical
Yes.
change, two substances or more than two substances can be reacting to form a new substances. For example, you have example of rusting. So iron is reacting with oxygen and water in the atmosphere to form ferric oxide, that is rust. And you can see I have written H2 also, but I have not specified how many molecules of water
Sir,
in it is, because it can vary from one rust to another. Yeah, Chagrika.
sir, it doesn't matter if the product is useful or not, right?
That does not matter. The product can be useful, product can't be useful.
But that
Okay, no?
doesn't matter, right?
That doesn't
Whatever
matter.
it
That
is, the only thing we need is the product.
exactly. Basically, it's all about observation right now.
Okay.
That is a different thing. Okay, what is the utility of different type of chemical changes? We are having utility of some chemical changes. For example, uh, like magnesium hydroxide, that is milk of magnesia, right? So it is an antacid that is used to cure indigestion. So it is having an utility. So that is another aspect. What we are, our
Okay, sir.
discussion is concerned with like how chemical changes is happening. Okay, so from here we will be continuing in the next class. Okay, now.